Okay, good morning. So we'll start today. The second in this lecture is on kind of psychological factors in perceptions of risk and mostly uncertainty. And I was not happy with the filming crew, so I brought my own crew. So we have another set of people shooting a picture here. So I want to remind you what we did last time and where I stopped. So I talked about issues about how to think about uncertainty, various ways of defining it, various distinction between various sources, internal, external, aleatory, epistemic, and so on. And then we spent some time about various methodologies for eliciting probabilities, for discrete events, and for fitting continuous distributions. Then talked a little bit about some empirical ways of assessing the qualities of judgments, internal consistency, stability, and so on. Spent some time showing you what the calibration curve is and how to analyze it and breaking it down into what we call calibration in large and resolutions, and so on. And then the last thing we did, we talked a little bit about some of the cognitive processes that go into judgments of probabilities and uncertainty, and how they sometimes can bias or push the judgments and making them less than accurate because of these pools of representativeness, availability, the predominance of anchors, and so on. I'm going to skip some of the things that I planned to say, because I'd like to leave at least the last half of this lecture to some illustrations of work in the context of climate change. But I want to say a word or two about this issue of motivation, which also Aaron alluded to. So generally there's this phenomenon that was very well documented by social psychologists that's called motivated reasoning. And motivated reasoning refers to the fact that it's kind of a Rashomon kind of idea, namely that the same evidence is interpreted and incorporated in people's judgment in different way depending on where you stand. It's just when there's a couple that's divorcing and they are arguing about property and about custody of their children, and every single piece of evidence that one side brings that goes against her, immediately someone can say, no, that's actually in her favor. In other words, that you can interpret and understand information in light of where it is that you stand and what is your position and opinion. And this applies to everything. It applies to probability judgments as well, in the sense that it's possible that people will perceive information and use information in ways which are consistent with their belief and expectation. And the one particular case that you'll see again people bring up is this idea of desirability bias. Let's call it bias for the moment. Namely the fact that when you ask people who are on various sides of a political divide before elections, what are the chances that your favorite party will win or the other one will win, people tend to overestimate the chances that their favorite party will win, or to overestimate the probability that their favorite team is going to win the game, or to overestimate the probability that they will have a successful career and a great marriage, and underestimate the probability that they will have debilitating diseases or have accidents and things of that type. So the way you ask about this, I ask people, what is the probability that you'll get cancer? Let's get a little bit serious here. You get cancer over the next 15 years, and they'll give you a number. Say, imagine now randomly selecting another person from the population, your age and your gender, what are their chances of getting cancer in the next 15 years? And if you do this for many people and many events, you can compare the probability judgments, and you see that people on average tend to assign to themselves lower probabilities. So I think this is a real phenomenon in the sense that it is observed. It's not quite clear that it is it's correct to call it a bias, because there could be very, very good reasons, right, for you to think that your chances are lower. And more than anything else, it's asymmetry in information, because you know much more about yourself than you know about the others, and you can, or about your favorite party or about your favorite team, and you can imagine how things that you do and preventive actions are going to work in your favor. So a typical example is that if I'm going to ask around here, who among you think that you are a driver, a better than average driver? And I think, I don't want to embarrass you because I know the answer. Almost everyone thinks that they are better drivers than the other. And how come, if that's the case, if everyone thinks they are better driver than the average, clearly there's a mismatch because there are these worst drivers out there. Who are they? They clearly don't self-identify. And if you want to think about how this kind of, this could be a bias, or your chances of, it could be a bias, you would ask, for example, what are the chances of you being in an accident? How that will happen, you think of the following things. You know of all the things that you do in order to be to make sure that you drive safely and well. You don't know, of course, the same information about all the other drivers. That's one component. The other component is that when you drive on a road for hundreds of miles and thousands of drivers go past you, most of them you don't pay any attention. The ones that stick in your mind and stay in your mind at the end of the trip are those who did something that was dangerous, who made them stand up. So in other words, made them stand up because of the dangerous action they took. So in other words, this kind of selective attention to bad actions or poor actions by others, as well as asymmetry in information, knowing more about the thing that you do correctly and well, that would induce this kind of performance, this kind of judgment. So we did a very nice, I think it's a very nice study to see whether there is how much of a bias there is. We did, before the last World Cup in football, we were at a summer school at the Hebrew University in Jerusalem, and we ran a study in which we did the following. We asked people to predict outcomes of, I don't know, maybe there are 20 games yet to be played in the next week. In other words, in the game between Italy and Mexico, who is going to win and by how many goals? And to induce desirability in a way which is independent of one's perceptions and one information and one knowledge and one opinion, we made team desirable through a random assignment. We simply, after people filled out all the questionnaires, we told them, so just to know, so that you know, in addition to the money that we pay you for participating in this study, if it turns out that Mexico wins, you win another $10. Or if it turns out that Italy wins, the other half of people, you win $10. So, and we excluded people who identify themselves, for example, in this case, of being fans of Mexico or Italy. So people who are otherwise neutral or as close to neutral, we basically induce desirability by saying there's going to be a prize for you if that happens. And so, in fact, what you show, you can see that there is simply introducing this kind of manipulating or inducing desirability, it affects the probability judgments by about 10 points on average. The other thing I would just want to mention is that, the theme of what I'm saying, things that shouldn't matter in principle sometimes do, is under this heading of structuring, framing, and labeling. I just want to give you one example of what I mean by that. So in the United States, the way automobiles are advertised and the way their information about them is presented has always been about fuel consumption, with how many miles per gallon the car drives. In other words, so a good car today is considered somewhere 27, 28 or higher. So for a given gallon of gasoline, how many miles can you drive? So my friends Rick Larrick and Jack Soll at the Duke Fuqua School did this study in which they basically showed that if you present people, you want people to induce people to make environmentally friendly and also from their perspective efficient choices about cars, and you ask them to make comparison how much do you think you'll save over a few years when you own an automobile. When you're comparing automobiles in terms of how many miles per gallon they get, most people are not very, very accurate. If instead you're going to present the same information in terms of gallons, not miles per gallon, but it is what do I want to say? Gallons per right. No, it is per money. How many miles per per gallon. In other words, if you think how many miles you can go to, it's not gallons per mile, it's miles per gallon, because the gallons are associated with a particular price. And so if you use this scale, which is the reciprocal essentially, but it's the same information that presented in a reciprocal information, people do a much, much better job of identifying correctly the effect of buying a more fuel-efficient car. In the context of climate change, there are some studies that show, for example, then you ask people their opinions, beliefs, and so on about climate change or about global warming, you get systematically different results. So this may not be just an issue of wording or labeling, but it could be more that in fact there's different information. I'm skipping here things about presentations of different graphical presentation. I don't have time to do that, and I want to talk a little bit about averaging or combining probability distributions, or probability information. So let me first remind you that I asked you yesterday how many canals you think there are in Venice. I collected. Can you see this? The output? Is it readable? Anyway, never mind. I can explain it to you if you can't. So I collected 22 people answered, and the distribution was kind of very bimodal. There were many people who there were. I can tell you exactly. There were 35%. Well, actually 45% of the people gave answer under 100, and then there was a bunch of people who gave answer which are greater than 400. But if you average all 22 judgments, these are not probability judgments, but they make the case. The mean judgment of the group was 187.4. The correct answer, at least to the book that I have in my hotel room, is 154. Okay. Now, so the average was relatively close. 154 is the true value, and the average was 187. What's more interesting is that if you can look, you look at the individual judgments, which are listed there in that frequency distribution. In this case, the average of the 22 people was closer to the true value than any single individual judgment. In this particular case, the mean of this group, that's not guaranteed to always happen, the mean of the group was closer to the truth than any single individual judgment. No one, in fact, I have also the same things presented in terms of deviation. So the deviation of the mean is 33, and none of the other individual deviations. Just one person was within 34, very, very close. So essentially, all this is to say is that there are something to be learned and something to be gained from combining together multiple sources. This effect, which now is known as the wisdom of crowds, based on a popular book that was published 5 years ago with this name, has a long history. In fact, the first paper that documents this is a 1907 paper by Sir Francis Galton in Nature. It's called Vox Populi. And what he did, it's really very funny if you look at it from these days. He, at a fair somewhere in England, I can't remember where, there has this huge, very large oxen, and he asked everyone among the participants to estimate what is the weight. Okay, and if you read the paper, it's just 2 pages, a page and a half in Nature. It basically, you say, today we run experiments, we recruit people to the lab, we pay them to come in. Galton charged people to come into his tent and to participate into his in his experiment, and people were, I guess, for the novelty, willing to do that. And what he has a result of about, I think, 750 people, and he shows that the median of the 750 people came within 6 or 7 pounds of the true weight of the less than 1% off. And again, it was the median of that was better than any individual judge. So when we are doing the same thing in the probability judgment, we are basically applying the same principles in a way that will give us additional information. So here's an example which I have to explain a little bit. What I have here is data that I got from Peter Jaslin, who's a Swedish cognitive psychologist. And what he did here has an experiment with several hundred people, but we only, in this case, use 60 of them. And what we do the following. They've answered several questions, which are all about mostly geographical and historical facts about Sweden and Europe, and then they stated their confidence. So, for example, what's the probability? Which of two cities was established earlier, and how confident are you? And then what he draws, this line that you see right here, the red line, is the calibration line, which actually you see is pretty good because, remember, the ideal is to be on the diagonal. And in fact, the whole point of this study, just parenthetically, had nothing to do with averaging, but has to do with the claim that some of the results that people are showing in the literature, how people are overconfident, are in fact artifactual, because people tend to choose, in these experiments, they tend to choose tricky questions that people would get easily tricked into answering incorrectly. For example, which city is northernmost, Rome or New York? Most people say New York because of their weather. Look at the map, Rome is to the north of New York. But that's kind of a question that people predominantly used in this case. And the argument that Peter and others had is that if you're going to do things of this type, but not by selecting items of your own choice, but defining, let's look at the domain of all cities in Europe, all rivers in Europe, and so on, and randomly select items, questions from that domain, then the type of question you're going to have is going to be more representative of the thing that one encounters in real life, and people are going to be better calibrated. But, so in this case, this is his calibration curve, and then when we got this data, we did the following. Instead of analyzing, in this case, the 60 participants individually, we first grouped them in groups of 3, and then in group of 6, in groups of 12. We calculated the average of the triple, sextuple, 12, and so on, and so on, and so forth. And then we looked at the calibration of these groups. And the result that you see is that, for example, look at the last one, which is when you average first all 60 subjects, and then you draw the calibration curve. And the results that you see is by averaging the more people, what you're doing, you are increasing the discrimination of this group in the following sense, and actually we can prove the following theorem. Under some relatively mild conditions, the more people you average, the more you're going to be in a situation that if the mean probability is greater than 50%, the event will occur. If the mean probability is below 50%, the event will not occur. So in the limit, you basically almost have a step function that says that if you have enough people, if the mean average of all these people is about 50%, it almost guarantees that this will occur. So in other words, in this particular case, what we are seeing how averaging increases the resolution of the crowd. I mentioned last time that I was in this forecasting project, and so what I'm using here some data from the forecasting project to kind of give you a sense of what averaging does. And so in this project, I'm going to show you in a moment some examples of some items, and I've selected only items that had at least 64 people responding to them. And what we are doing, we are analyzing the distribution of probabilities of individual judges, or taking judges and combining them into pairs. I've learned all these new words, let me not waste them. Tetrads, octads, and so on. And so what you do, you put them all together in groups of this size, calculate the mean of the 4, of 8, of 16, of 32, and so on. And then once you calculate the mean, then you want to see what's the distribution of judgment. And in this particular case, I don't have time to go into all the details, but what we are doing, the metric in which this is presented is a metric of a probability score, of a Breyer score, which is such that a perfect judge will get 100. In other words, if a person always identifies whether the event happens or not, and gives it 100 if it happens and 0 if it doesn't. So perfect score is 100. Worst case scenario is 0, someone who always gets it with 100% confidence wrong. And a chance, someone who randomly selects answer or someone who tosses a coin for every item is going to get 75. And the reason this is not 50, because the scoring, this is a Breyer score. So this is squared. So therefore, 75% is chance. So there's a subtle point is that if you want to see what happens if you have individuals or dyads or quadruples and so on, if you have more people, you only have not only you have more people, you also have more information. So you want to deconfound the sample size from the information content. So what we do in this case, we take always 64 people. So all the plots I'm going to show in a second are 64 people. But in one case, we are look at this item right here. In this case, this is the distribution of all the 64 judgments, individuals. Then we take the 64 people and create 32 pairs, and then you look at the distribution of probability judgments of 32 pairs. You take the same 64 people and combine them into groups of 4. So here is this box plot is the distribution of the 16 judgments of size 4, and so on. Now, since this is done, so the pairing or combining is done randomly, we repeat this bootstrapping procedure 500 times. And so I want to give you a sense of what happens when you are looking at a larger number of people, because that will give you the two or three principles that emerge from this work. So in this case, for example, it simply shows that in some cases, it really doesn't matter very much, because there are some items that are so difficult. Remember, 75 is chance. And in this case, if you look at this item, even after you average 64 people, you get nowhere near to chance level. This is an item that practically everyone got wrong. And sometimes in the absence of pure information, simply taking numbers will not compensate for it. There are items that are relatively easy in the sense that everyone predicts them correctly. And again, in this case, if you just took a random individual from this 64, or you average 32, or you average all 64, it really, again, doesn't make much difference, okay? In other cases, the change is more pronounced. And that, for example, you can see how, at least, I think in both of these cases were selected such that if you look at single or individual, the mean of the distribution is below 75, but once you get to higher, you get above chance. But what you see also is this idea that it's really the gain from combining people is not unbounded. In fact, most of the action, the way these are on the x-axis on a log 2 scale. So every single step means the samples, the number of judges is doubled, right? It's 1, 2, 4, 8, and so on. But typically, when you go beyond 8 or beyond 16, there's not much to be gained. So most of the action happens when, if you have more than 4 or under 16 people. But so this may not be so. That may not sound as dramatic and as important as as some people would like you to think. But I think there's another point that people often miss about combining or aggregating probability. Yes. Yes, there was a question. Okay, thank you.
Just curiosity. So here you're combining individual judgments and averaging them. Do you see similar or related effects if you put 8 individuals together and ask them to make judgments?
Okay, I'll talk about this in a second. So in other words, what you're asking the question about interacting group versus nominal mechanical group, which I'm showing here, and the impact of independence between or lack of independence between judges. I'll talk about this in a second. I just want to make this last point that this is not very striking in the sense of increasing the quality of the probability tremendously, but the averaging, I think, key effect, and that's something that you'll find also in many of Bob Winkler's paper, who wrote, you can say, the book on aggregation of probabilities, is that if you think of the worst case scenario, so this is a spline fitted to the 5th percentile, right? If you look at what happens to the worst case scenario, this improves tremendously. So by averaging people, you may not always get, on average, a much, much better result. What you're doing, you are reducing dramatically the probability of getting it very, very, very wrong. Okay, so you see that's kind of clear and asymmetric pattern in this result. Okay, so now there's another, so two results here. One, averaging is beneficial in the sense that it increases, or combining, I should say, it increases not calibration, but resolution. It reduces the possibility of getting it altogether wrong. And you typically get most of the action by averaging between 8 and 16 people. The other question is what it is that you can assume about judges. Okay? So in this work, in most work on wisdom of the crowd, the idea is that people are performing individually, independently. They create their judgments without communicating with others, and then the combination is done mechanically. Okay, that doesn't mean, so there's a subtle distinction here. The fact that people operate individually and without communicating to each other, they are experimentally independent. That doesn't mean that the results are going to be uncorrelated. Most people, if you look at the numerical value, they still are going to be correlated in a statistical sense, but my judgment is not going to be tainted by your opinions. And through theoretical work and through simulation, you can, again, very easily, and people have also shown it analytically, you can also show the following, that the higher the correlation between judges, the more judges it takes to achieve the same effect. So in some sense, you'd have to use more people who are correlated or dependent with each other to achieve the same effect as you have n people that operate individually. Now, the issue of what happens when people interact with each other in group, just a second, it's really, in some sense, it's a corollary from that, because by being them together, they're going to be somewhat more correlated. But it is more subtle because there are, I think it varies on the nature of the groups and how they are created and how they exist and so on. So for example, in our forecasting competition, the team that did best actually had groups that were communicating, but it was all asynchronous on the web. In other words, they had a page, and they would say, I made a judgment, and they would share with each other some of the arguments, and these groups did better than individuals. If you put a group in a team, face-to-face and conversation, this could have actually, in many cases, less undesirable or less desirable effects, because there are people who take over. There are people because they are perceived as being the expert, the leader, the boss, and so the hierarchy, either perceived or existing, may, in fact, have a negative impact. There are ways to go around it. There's something called the Delphi method. Some of you may have heard about it, or if not, you can read about it. It's a way of trying to extract most of the positive components of group interactions and eliminating the negative one, because it's done round by round, and people don't talk to each other, but you get a round of estimates, and then they're being communicated to everyone else. People are given opportunity to revise and so on. And so you try to take away some of the group dynamics that can have a negative impact. You had a question?
Yes, thinking about interaction that arises without communication. For instance, people know what is the aggregation method. They might internalize that this will have an effect about the future results. So for instance, we should take strong action.
Right.
Well, I might want to give a biased answer because I know that this will have an effect.
Yeah, I mean, that's true. Absolutely, you're 100% right. One other thing, I mean, I'm not going to talk about it in detail, but so I keep saying aggregating and averaging interchangeably. Actually, for probability judgments, you can improve all your results if you're doing the aggregation not in the scale of probability, but if you're transforming the probability by stretching them, and typically, okay. Oh, actually, tried the board this morning. So essentially, something that typically works very well is to take the log odds. So you take, and then you take the mean log odds of the group. And what the log odds are doing, like the regular arc-sine transformation, what they are doing, they are stretching the scale. It's no longer between 0 and 1. It's between minus infinity to plus infinity. And most of the action of the transformation is at the end points. Because if your p is between 0.2 and 0.8, it really doesn't make much of a difference. But the extreme value are stretched out, and therefore, when you are combining them, right, and when you're averaging log odds, then extreme opinions are overweighted relative to the other one. So you transform everything to log odds, you take the mean of the log odds, and then you do the inverse transformation back on the probability scale. And this is just one of two or three different ways of doing the averaging. Okay, I want to talk about a few other topics. Now I'm moving a little bit from the topic of judgment. I'm talking about the communicating results of judgment. So there's a very interesting component, which I'm going to talk about it later, is that people can use, when communicate probability, you can use number, you can use ranges, you can use words. And people actually, you see this in various surveys and studies, prefer to use words to communicate. I think it's very likely. I think it's practically impossible that will happen. So they prefer to use words when communicating to each other, but they have a preference for receiving numerical information from others. Okay, so they have this kind of switch. And we've done this with survey. Karl Halvor Teigen at University of Oslo and Boone have done it with analyzing all kind of other communication, patients and physicians, and so on. Now, in some sense, people like to receive precise information, and so that you can extrapolate and say that there's going to assume there's going to be an unconditional and universal preference for precision, which actually turns out not to be the case. In fact, we think that if you're going to be precise in cases where clearly the data doesn't warrant that precision, this is going to backfire. So if someone says the chances of an abrupt drop in the market in the near future is 0.2348, in other words, it's an ambiguously defined event because I didn't say exactly what abrupt and what near future is, and yet I'm attaching to it such a precise information, this is not going to be credible and believable. And in fact, there's good evidence that people people have expectations of what will be the level of precision of communication as a function of what they perceive to be the nature of the events and the precision of the events, and they act accordingly. So there's this study, very nice study by Ido Erev, where he sets up a judge advisor system where some people have access to information and they communicate it to others, and others have to make decisions without seeing the information, but just based on the advice. And you can create two groups in which there's one or two judges, and there are many decision makers, and you can create a situation where the payoff of the decision makers of the function is one that is maximized by unanimity. So if everyone among the decision makers agrees on, let's choose action A, the payoff of the group is maximized. On the other hand, if you have situations where the payoff of the group is maximized by diversity of opinion, okay, and what you see is how gradually over the course of the session, people, the judges, learn that in a context that reinforces unanimity, you need to communicate numerically, precisely. In a context that reinforces and values and rewards diversity, it pays to always use words because they induce more diversity and more variability. So Ning Du, who's a former student of mine, and she's in accounting, she's in business, came up to me one day and said, there's this peculiar phenomenon that I don't understand. Financial institutions are not required by law to issue any forecast of how they would, right? So there's absolutely no regulation to do that. Yet many, many, many firms provide quarterly or annually predictions of what will be their EPS, earning per share. So, they have the option saying Intel or Microsoft can say, we anticipate in the next quarter our stock is going to earn $6 or more likely 6 cents per share. And when you look at this, you see that most firms choose not to tell 6 cents or a precise number of cents per share, but rather to provide a range of value, or simply say it's going to be more than or it's going to be less than. And so in other words, they communicate imprecisely to their investors. And you wonder, why is it that they do that? In other words, how can they get away, right, with being so imprecise and vague, and whether the public understands it? So we ran a couple of studies using MBA students mostly as participants, and we showed them stories. Here's what we did. We actually took text from press releases of various firms, but I took away all the identifying information, right? So there's a paragraph. We said, this firm is in this sector, they do that and that. That's their business sector, and their prediction is that for next quarter, they're going to earn 6 cents in some cases, or between 4 and 10, or between, ranges. And to see whether people would be more willing to buy, we'll find some of them more credible, and so on. And so what you see that people actually in this context, in a financial context, they think that the nature of the event and the information that's available to the people who are making the prediction is such that precision is not believable. It's not credible. So in other words, they value more, they are willing to pay more to buy stock in companies that report relatively narrow ranges of uncertainty. So in other words, there is not preference for precision, period. There is preference for a level of precision which matches what people expect to be reasonable and credible in a particular context. Okay, so I want to say 10:30, is that long? Okay, so I'll do more, maybe 20 more minutes. So now I want to talk a little bit about actual decisions under uncertainty, just to give you a sense of how we as psychologists approach it slightly different. And clearly, I'm just using as an example binary situation, binary gamble. So the top, the item, the commodity, so to speak, is a binary gamble. You win X with probability P, or Y with probability Q, where the two probabilities are additive. And this is just kind of remind you of the history of decision making, starting in the upper left corner with the expected value, where you use probabilities as given, values as given. And then what happened over time, the model has relaxed and relaxed and relaxed by, through Bernoulli, the St. Petersburg paradox, not values, but the log of the values, and then von Neumann and Morgenstern utility, and prospect theory, the value function, which I'll explain in a second. So we have become less and less restrictive, and then we've also went in terms of relaxing the model from probability as given or objective to subjective probabilities, and through what I'll explain in a second to be decision doing. So this is a table which is 3x4, and in fact there's a model, or at least several models in each one of the cells. I just listed some of them to give you orientation. And I want to show you in a moment what prospect theory, which is the most recent behavioral theory of that, does, how it deals with this decision problem, how it's different from expected utility or variance of expected utility. And then I'm going to show you in a second how you can extend prospect theory to situations where the probabilities are imprecisely stated. So in prospect theory, essentially what you do, the overall value of a gamble is, as you see, function of the p's and a v of the x, decision weights, which are functions of the probabilities, and values of value functions associated with the outcomes. But the key, so there's nothing new there. It's the same bilinear form as the expected value, just with some functional bells and whistles. But what's interesting and what's new in this theory is the assumptions or the property that we attribute to the two functions, the value function on the left and the probability weighting on the right. Is this something that everyone knows? Oh, so everyone knows. So should I skip this? No, okay. Thank you. That was the right answer. Thank you. I know. So what is special about, let's look at the utility, at the value function on the left. How is it different from a utility function? So it assumes concavity above the threshold. It assumes convexity below the threshold. But what is the threshold? Unlike all expected utility theories, where everything should be considered in the context of one's overall wealth, okay, in an absolute sense, prospect theory, the value function, starts by everything being encoded as a gain or a loss as a function in reference to a current status quo or your current reference. So in other words, what really matters, the distinction is between whether this is a decision involving gains and gains, losses and losses, or gains and losses, but it's all in terms of immediate gains and losses. And you can see that why this is meaningful and correct psychologically, because if you tell people, here's a choice between two gambles, which one do you prefer? That's one group. Or maybe the same people, but half an hour later, tell people, you present the same, you should take the same gamble, subtract $100 from everything, and tell people, by the way, you have $100, this is yours. Now, you can also, choose between these two, and now, because you subtracted everything, you put everything in the domain of losses, they will reverse choices. If you tell people, we're going to take away a large sum, and then make, again, the choice, people are going to make different decisions. So it's not that if you tell people you have 100, but now choose between, or choose between these two gambles plus 100, they are going to choose differently as a function of what are the distinctive things that are being compared, right? And they are going to encode everything in gains and losses. So the key realization, the key insight is that everything is coded in terms of gains and losses, not in terms of wealth. And the other one is the distinction between the shape of the function plus the principle of loss aversion. Namely, the fact that the slope of the curve of the value function in the loss domain is steeper than in the gains domain. So, the sentence from the 79 Econometrica paper that everyone repeats is basically, losses looms larger than gains. And the way you see it, how would you prove this? Ask people to choose between symmetric gambles. In other words, would you rather bet on a 50-50 chance to gain or lose 10, or would you rather bet on 50-50 chance to gain or lose 100? And most people stay away from the loss 100 and favor the loss 10. In other words, the probabilities being the same, the gains and losses being symmetric, as the amount to be won or lost is increased, people become more and more loss averse. And so this is really just loss aversion, which is not the same as risk aversion because it doesn't involve in any way risk in a von Neumann-Morgenstern context. So that's one feature of the function of the theory. The other one is this function, which is the decision weighting function. It's a decision weights as a function of the true probability or the inferred probability. And you see this induces nonlinearity in the decision weights. The decision weights are essentially a monotonic subjective transformation of the probabilities that capture the weight that a particular probability plays in this particular decision. And notice that it's no longer a probability. In other words, if you look at this function, you can have 0.2 and 0.8 that have decisions weight that don't add up to 1. So these are no longer subjective probability. That's what we refer to them as weights. And they capture things such as overweighting of low probabilities, underweighting of high probabilities, relative, maximal sensitivity to probability near the edges, and relative insensitivity in the center. So that's essentially, that's prospect theory. And, you know, you don't have to, but this is one particular instantiation of what the form of this function. So the value function is a power function. For the losses, it is also a power function, but this lambda right here is the so-called loss coefficient. In other words, that tells you how much more weight losses are, how much more severe losses are than gains. And typically, when it's being estimated, it's in the vicinity of 2.25. In other words, that losses are twice, on average speaking, more severe than gains are pleasurable. And this is one particular form, not the only one, that you can use for the weighting function. You can see this function is that the weights are a linear transformation of the probabilities in the log odds matrix. So in other words, you take the log of the probability, multiply by gamma, add a, and you get the function. Okay? So that's just a way to capture the curvature of the function.
I didn't get that.
Which, this form?
Yeah, the last one.
So essentially, what this is, this amounts to f. Oops. F of log p over 1 minus p equals to a plus gamma log of p over 1 minus p. That's just one function. There's a more elegant function by Dražen Prelak, which is linear in log-log, and it has a nice property that the crossover point where you go from overweighting to underweighting is precisely at 1 over e, which it's just so beautiful, but I mean, they're very, very hard to distinguish empirically. I mean, you have to have hundreds and hundreds of decisions to really to be able to tell them apart. Okay, so this was kind of almost just to give you a little bit of background, because I think that one of the problems with many uncertainties in climate change is that you cannot really identify the probabilities with the precision that would be required to be placed into, you know, an expected utility or expected value or a prospect theory model, right? And so does everyone know Ellsberg's paradox? Everyone? Okay, so that's exactly the idea that I'm trying to capture, namely that, you know, just you have Ellsberg's paradox, which means that, which the way I summarize it in one sentence is that, you know, it's not enough to know a probability and a value in order to make a choices in some context, but there are other features like the precision of probability in this case that would make a case. So people talk a lot about, in Ellsberg's paradox, talk about, you know, avoidance of ambiguity, which I call vagueness. When I say avoidance of vagueness, I mean exactly what people mean by probability of ambiguity. But first of all, I want to show you some data to basically make sure that you all understand that although this is the model response, yes, it is what happens in most cases and for most people, this is far, far from being universal. Okay, so here's an experiment where Karen Kramer, a former student of mine, and I did. And so, I don't know why I say this. Anyway, if you look on the, oh, thank you very much. I'll hire you. Okay, so if you look on the left-hand side, which is the classical Ellsberg setup. So we have one urn where you know precisely the composition, how many reds and how many black balls, and another urn where you just know there are red balls and black balls, but you don't know the composition. And we ask every person, you know, to make a variety of choices among pairs of this type, and we were able to classify at the end of the day every single individual choices as, actually there were many replications, you know, there are not just one example, but there are many, many examples. Many cases in which people, we could classify people according to whether they succumbed to Ellsberg paradox or they were or not, or they are totally inconsistent and unpredictable. And if you just, let's look at this, you see that people about, this is percent, about 35, between 1/3 and 40% of the people actually consistently fall for the Ellsberg's paradox. In other words, they always given a choice between an urn with precise and imprecise composition, they choose the one that is more precise, and therefore this is the Ellsberg's paradox. Then the second more prevalent pattern are people right here who are consistent. In other words, they are perfectly in line with expected utility. They choose, the precise in one and the imprecise on the other, therefore clearly according to expected utility theory. Then there are people who are inconsistent in the sense that they have a choice in one presentation, but they're indifferent in the other. Then there's a minority of people who are basically say, I don't care, I don't care, I don't care. So these are the ambiguity neutral people. And there's a minority of about 10% of the people who actually are ambiguity seeking. They always, whenever given the choice between two urns, on both occasions, they choose the imprecise one. So the moral of this picture is that ambiguity aversion, everyone is ambiguity averse. Ambiguity aversion, a la Ellsberg, is the mode, but it is a weak mode. It is a mode that characterizes less than 40% of the people, and there's a considerable minority of people who are consistent with expected utility theory and reverse, and people who actually have reverse preferences. So I think it's a mistake if you want to include ambiguity aversion in a model to assume that it is something that is a given and is common to everyone. You need to model it just the way you model various degrees of risk aversion, various models of ambiguity aversion. So we got interested at some point in the question. I'm sorry.
I don't even quite understanding the paradox.
Yes.
So it seems as though if I wanted to make a decision and I had more precise information, wouldn't that be beneficial for me to make a decision?
Okay. So the paradox, it's not a phenomenological paradox. There's nothing. You're asked to choose between two urns. One is a known composition, one is an unknown composition, twice. Once, which one did you choose if a red ball wins money and a black ball doesn't? And the second time, what do you do if a black ball provides a reward and a red ball doesn't? So phenomenologically, there's no paradox. You can choose any way you choose. It's a paradox only in the context of a utility theory, because if you put these choices together, it means one of two things. Either, if you assume that you have a constant utility function, that the probability you assign to red and blue don't add up to 1, which is a violation, or if you insist that they add up to 1, that you have a different utility function from winning $10 because you got a red ball, than from getting a 10. So it's a model bound paradox, not a phenomenological. Okay. So we got interested in. Okay, I'm just to give you a sense of what we did, and then I'll move to the other one. In this issue of which kind of precision or imprecision is more important, about probabilities or about outcomes. Okay, so think of the following situation. There's a new medication that's been, in fact, I started thinking about this when I got my yearly flu shot, and I got back from the health center to my office, and I was reading the information sheet, which I should have done before I got the shot, but I was reading it, and they were talking about side effects and severity of side effects and so on. And I was puzzled by the way this was phrased, because they were very imprecise about what's the probability there will be some complication or side effect, and how severe it's going to be. So what we started thinking about is whether it makes a difference to people. It's more important for people to have known the precise probabilities or the precise outcomes associated with decisions. Okay, so you can think of, we are developing a new technology, and we realize that it has some probability that it will have side effects, but the probability is not known precisely. It's somewhere between 0.07 and 0.15, so imprecise probabilities. And also, it's not quite clear what's going to be the severity of such of this outcome, of these hazards. So it could be anywhere between 2 million and 3 million. Okay, so these both can be imprecise. And your friend Howard Kunrater and Jack Mazaros have done work on this with insurance underwriters, right? Because to see what it is that matters more to insurance underwriters in this imprecision about probabilities or about outcomes. But all this work was lacking a control, a way of telling whether two levels of imprecision are equally imprecise. So we developed this particular way of thinking about it. So here's a gamble that has a 5% probability of winning $75 and has an expected value of $375, right? Now, let's say I'm developing a range of probabilities, so between 0.3 and 0.7, and I'm developing a range of outcome between 0.45 and 0.105. And I can always choose values of ranges of probabilities and outcomes that are such that that these gambles these three are matched. So for example, if I have 0.05 and outcomes between 45 and 105 span a range of expected values between 225 and 525. So this is an expected value that you strictly to imprecision in outcome. On the other hand, if you have a fixed amount of 75 and the probability goes from 3.3 to 0.7, you get exactly the same range. So we would say that these two gambles, 0.5%, 5% to win an amount between 45 and 105, and the gamble that gives you 75% dollars with a probability between 0.3 and 0.7 are equally imprecise, are equally vague because they span the same range of expected value. And furthermore, to compare them, you can always use the 5% to 75 as the precise component to which they are to be compared. Is this idea clear? Okay. So that's the way to basically calibrate imprecision on the two outcomes. And just to give you I'm going to stop here and go to talk about the other stuff. These are results from our paper. This is Management Science 2005. And essentially what you see, we did this for gains and for losses, and you get a pattern that is really kind of relatively complex and complicated and not very, so for example, it's complicated also because we insisted of doing both certainty equivalence and simply choices. But essentially what you get, and I'm running out of time and I'm happy to send you the paper and to talk to you about it. Essentially what you have different pattern when you ask people to choose between gambles and to make certainty equivalent. That's what we refer to this sometimes as preference reversals. And essentially probabilities matter more in the context of choice. Money outcomes, the monetary outcomes matter more in the context of setting certainty equivalent. And in some cases you get vagueness avoidance, in some cases you get vagueness seeking. So I apologize for being so poor at planning my time. I'm going to stop my presentation here, and I'm going to skip to another one, which I really think has more to do with climate change's work that I'm kind of very happy. Okay. All right, so I want to talk now about communication of uncertainty in IPCC reports and empirical results. So has everyone seen this table? Has everyone ever looked at an IPCC report? Okay, so the IPCC report, I'm not privy to what went on behind closed door and how this was arrived at, but the way uncertainty has been communicated in IPCC has changed from across the various assessments. In the last assessment, there are two scales. One which basically describe, I think, the quality or the weight of the evidence, and the other one that talks about probabilities and uncertainties. And all the authors are. There's a booklet with instructions for the authors, which is they are told if you have probabilities in this range are going to be communicated in this using these words. If I understood the last presentation yesterday, the 66% was chosen because this is what likely mean in that particular context. So this choice, which I don't want to criticize. I mean, I'm not sure that if I or anyone, the smartest JDMer, would have been asked to come up with a different way of doing it, would have come up with something different. But there's a lot of work that was done in judgment decision making on words, on linguistic probabilities. And here are some stylized facts about this. First of all, people have very, very distinct and different lexicons of uncertainty. So we ask people, we've always done in experiments, we're going to do a lot of choices involving probabilities. Please choose 7 or 11 words that are best for you to kind of span the whole range of probability. And the 11 or 7 words that that people use vary dramatically. Sometimes you get over 150 words in a sample of 25 people. And English is particularly friendly in this sense because it allows you to make up or generate a variety of words, by using qualifiers, adverbs, and so on. The way in which words are interpreted, it's personal, it is subjective, and it is elastic. It can be, and is subject to context. In other words, there are very famous stories, which some of them may be true, some of them are, I don't know. Right now they are repeated so many times you have to treat them as true. For example, before the invasion of the Bay of Pigs, the CIA told President Kennedy and his cabinet that if the landing is successful, then it's likely that local forces are going to join in the American invading force. Okay, nothing happened. In the debriefing, the word, what do you mean by likely, came up. And at that point, apparently, the legend goes, the political decision maker, political decision maker said, they assume it meant between 0.7 or higher, and the CIA said, oh, likely, it's around 0.4. So whether they meant it or not, or whether this is what they call self-serving interpretation, okay, it really doesn't matter. The point is that if you ask people, if I were to ask this questionnaire here and ask, what is the probability that best describes the word likely, I can guarantee this because I've done it many, many times before, including with intelligence analysts and other experts, that the probabilities were assigned to the word likely would probably range between 0.5 and 0.9. So there's going to be a large individual differences. Some of them are innocuous. They are a spontaneous way in which you think about language and the way you use language. Some of them may be a function of what's your native language and things of that type. And some of them, they may be a function of the context in which you operate. The other thing is it's extremely difficult to legislate language. I mean, here's a study that my colleague Tom Walston did with national weather forecasters. So these forecasters have a table like the one we saw a moment ago, which they use on a daily basis to make predictions about precipitation, temperature, and severe weather events over the next 48, 72 hours. Okay? So when they go to work, or when they sit at their desk and they work, for them likely has a particular meaning, which is exactly the same like everyone else who sits in similar offices all over the country. Now, what Tom did, he administered to weather forecaster a questionnaire that used this kind of words, likely, unlikely, very likely, and so on, in totally different contexts. Like, you go to your physician and you're being tested, and he tells you it's likely that you're going to need a knee operation in the next 3 years, or things of that type. So in medical context, personal context, and so on. And in each one of these questions, he asked them, what do you think it's meant by likely, unlikely, and so on? The moment these people who have a very well-defined and precisely defined word meaning of what likely means in their daily life at work were asked about likely in different contexts, they basically ignore that lexicon that was imposed upon them, and they reverted to the regular colloquial interpretation. So all these things together means that when IPCC says, here's what likely means, it may create, in some sense, an illusion of communication because, well, there's a table, but do people follow the table and do people understand this the way it was intended? So we ran this study. And I'm going to show you the results. Actually, we ran 2 studies. By now, I ran many studies, but I will talk about one, and then the one that we have it's published in Climatic Change 2012. So essentially, we have in this particular case a national sample of about 550 people. And what we did, we extracted 8 sentences from the IPCC, from one of the executive summaries of the IPCC report. And they were such that there were 2 sentences that included the word very likely, 2 that included likely, 2 unlikely, and 2 very unlikely. And people were presented with these sentences, and they were asked under various conditions, which I'll explain in a second, in an experiment, to tell us what is their best understanding of the word. In addition to doing this, numerical assignment to words of IPCC pronouncements, we also administer a bunch of questionnaires that tested, not tested, not the right word, that measured people's belief in climate change. So the scales such as how their degree in believing global climate change, personal experience with climate change, their perception of causes, the perception of consequences, and a few other things which are not listed here. We also, I think that's in response to someone asked me about it yesterday, we administered a scale of numeracy, which I'll show you in a second, to see how numerate these people are. And these are going to be used as covariates or correlates of people's interpretation of the word. Now, here's the key interpretation. Here's the key manipulation of the experiment. We have 3 groups, control, translation, and our proposal of verbal numerical. So this is a screenshot of the experiment. There's a statement, reconstruction of climate data from the past 1,000 years, blah, blah, blah. It's unlikely. And so you can then communicate on a scale of 0 to 100. What do you think unlikely means? That's the control. That's someone who simply picks up, has no idea that there's a particular meaning, and simply reads it. Then another example, which is basically people always had this in front of them. I mean, the translation table, I can't remember whether in this particular experiment it was always there, they could not avoid it, or they had to click on a button to open a pop-up window. But in other experiments, it was always there. And then the third one, the one that we are proposing, was that every time a word is presented, it's always accompanied by the range of values which describe it. So essentially, it's not more information, it's the same information, but in a different format, and one that explicitly reminds you of what likely is. And there's a reason to prefer this, which I'll explain later. Okay? So here, in some sense, this is both the bad news and the good news. Well, the bad news and the somewhat good news. Since there are 8 items, you can calculate for every single individual how many of the 8 occasions were in which he or she had to say what's the numerical value of that word. The numerical value that they assigned was in compliance with the IPCC guidelines, right? So how many times? I mean, someone who read it carefully and understood it perfectly, you would expect them to be always at 1. Because that means that all your 8 items were within the prescribed range. And these are the cumulative distributions of consistency in the 3 groups. So the depressing thing is that the overall rate of consistency are very low. Most people do not interpret the words as intended or as prescribed by the table. It varies from about 21 to 20%. And our improved scale increase it from 20 to 30%. The somewhat good news is that you see this green line, which is of this joint verbal numerical scale, stochastically dominates. It's clearly much, much better, increases by 50%, but it still doesn't get you anywhere beyond 30%. In fact, here are the mean values assigned to very likely, unlikely, likely, and very likely for the three groups. And remember, very unlikely should have been less than 10%. It's on average interpreted as 40%. Very likely should have been over 90%, on average interpreted at 60%. Okay? So all the interpretations are very regressive, much, much closer to 50% than intended. You can see, again, that's the somewhat good news. The reassuring news is, well, not reassuring, but the better news is that this green light, which is the improved presentation, is the one that differentiates best between the words, but it's still far from being perfect or desired, or as desired. Here's an interest. Now I'm taking this for a given. People are misinterpreting these terms. They are much, much more aggressive, and it's a very, very typical. I mean, you can assign this to misunderstanding, to a variety of other things, to discounting. You discount the information, you treat it more. I mean, like you go to a physician, say, oh, you have 60% or 90%. You have this disease. You have to do that tomorrow. Then we'll go home. He meant 90%. Maybe he really meant 70 or 90, so kind of not take it as extreme. But the other interesting thing here is the degree to which the numerical values associated correlate with people's beliefs. And you see, for example, in the first, I should look at this too, okay? So if you see in the first line, the numerical value that people assigned to the various words correlate with the degree to which they believe in climate change, to the degree that they have personal experience with climate change, and so on. So clearly different people who have different, that's the motivated reasoning idea that I described earlier. People who have different beliefs to begin with are basically interpreting results accordingly. Here's what since people ask me about numeracy, here's what a numeracy items looks like. It's a funny scale. It's not a mathematics scale. It's a scale of items or questions which are of the type. Look at the baseball and bat. Number 3. A bat and a ball cost $1.10. The bat costs $1 more than the ball. How much does the ball cost? Okay. So what's the answer? I don't want to put you on the spot, but all these items have two types of answer. They have the correct answer, which in this case is 5 cents, right? And there's an intuitive answer that jumps at you, which in this case is $1, okay? Or 10 cents. Okay, or look at number 5. So this is a lake that has a geometric progression that doubles itself, and it's half full. I mean, it takes 48 for the patch to cover the entire lake. How long it will take to cover half of it? The correct answer is 47, of course. Many people answer 24. Okay, so these are. I don't have time to talk about if you read Danny Kahneman's book of slow thinking and fast thinking about system 1 and system 2, but that's exactly what it is.
Well, they interpret it as cognitive perfection, and you say it's numeracy. And numeracy is often literacy is often measured differently. So
Well,
why you interpret it that way.
Okay, so you're now getting to see how psychologists argue with each other. I mean, we make up these things, and we argue about exactly how to label them. So yes, you're right. So this is one of several popular scales of numeracy, which in this case there are many more. Yeah, and this is I think something that we put together by using Shane Frederick's item and some of Ellen Peters' items, but there are other items that are longer and more broad. But that doesn't. For my point is that it takes 5 minutes or less than that to answer these five items. People get scores depending on how many items they answered correctly. And so here we are see on the x-axis the numeracy score. You would like to see 0, 1, 2, 3, 4, 5. Unfortunately, there are so few 4 and 5 that we combined everything that's greater than 3. So, and the point is the following, is that now you're looking again at the consistency rate of the three groups of presenting the three different ways of presenting the IPCC items, and you see that the people who are high numerate, you know, they are the ones that benefit most. They benefit most from having this additional information about both the numerical and the words, but no one suffers from it. Okay, so we saw that it's going to be more powerful. So anyway, so that's okay. Here's the most depressing result: is that if you simply look, now this is across all. This is across all the responses, all the groups. It doesn't matter how they are presented, but you simply classify groups based on their political ideology, okay? And see how they interpret the words. And this is in the United States, it's a national US sample, and you see that the bottom line, the red line, these are people who identified, on the 7 scale, there are, where 6 and 7 are highly Republican, so these are people who are Republicans. These are people who identify themselves as Democrats, and these are people who are in the middle of the scale who call themselves independent. So in other words, whether your ideology is that you are Republican or Democrat makes an average a difference of 15 or 20 points in the way the probabilities that you assign to numerical to these words in the context of the IPCC. What are the results? The public consistently misinterprets the probability statement. What I don't know, I mean, and I'm talking this, and I'm serious about this, because I talked to some people who are, a small number of people who are authors or co-authors on IPCC terms. So all this is predicated on the assumption that, you know, since people tell writers, this is how you should be using this word, they actually obey this rule. And when people write likely, they really mean something greater than 66%. I talk with some people who are authors or co-authors. I don't get a sense that they take this that seriously. I don't know, you may have different experience. But if they do, then mean that the public, the readers, interpret the results less extreme than intended. In other words, this particular mode of communication is one that could have the bottom line implication that people are not going to take the more severe statements as extremely as intended by the people who write them. So there are large individual differences, and they are associated with a variety of perceptions and also ideological component. There's the reason we are proposing this scale, which the dual verbal and numerical scale, is first of all is that you're sacrificing very little. All you have to do is have to accompany every word with its description, with its numerical description. It works to some degree. I mean, not as well as you would like it to be. It's not that all of a sudden everything is precisely as intended, but it works much better. And I think that it has another, what I take to be a very, very positive component, namely that it would allow you to go away a little bit from that very rigid table. Because in some cases you may want to say likely, and by likely in this case I mean just by the table greater than 66%, but in some occasions we may want to use likely to be more precise. I have much more information and better information about this particular statement, and I can say likely, but in parentheses, in this case, I mean between 70 and 85%. Okay, so I think there'll be much more flexibility to both maintain this, the current structure, but to augment, to complement the words by numerical ranges, and that will allow much more flexibility in communications. So last year, I got 2 years ago, last year, I got an NSF grant, and I've done this now with 10,000 people all over the world in about 20 languages, okay? And what you see here, I mean, we're just analyzing the data. Come to Barcelona for SPUDEM in August, you'll see all the results. So what you see here is basically results from all the countries that this is basically the improvement in compliance with the IPCC terms when you administer this in all these 24, 25 classes around the world. There are differences between various countries. Not all of them we understand, but the one thing that you see is that in every single country, adding the numbers to the words improves the quality of communication. So I don't know. So maybe this will get IPCC's attention. I mean, I don't want to get. I'll probably skip all my other examples because I'm running out of time and I want people to ask me questions. Is that okay? So, but I don't want to give you the impression that everything that we do in JDM or in psychology of uncertainty has this flavor of being, let's run this experiment, let's see what the data do, and that some of the things that we are doing are really much more deeply theoretically driven. So, for example, since we talk about this word, let me show you how you can do a lot of interesting theoretical work with probability words. So what I'm showing you, we are borrowing idea from fuzzy sets theory. Everyone knows what I mean by that? You know what set theory is? Okay, so in set theory, every exemplar, every event, you are either a member of the set or you're not, right? So membership in a set is all or none. It's a 0-1 function. The idea of a fuzzy set is that membership is gradual. So for example, if I'm asking, is David a member of the set of middle-aged men? And well, the answer is yes, right? But in principle, you can see that if you are to see as a age on one, right, and membership in the set, you know, it's not that people who are middle-aged, you know, if your age is 45 and a half or higher, yes or no, but there's a degree of membership in the set, which in this case is a function, increases a function of age, is a function of age, and you know, you can think of, you know, is someone, a tall person, and so on. So because language is in itself imprecise and fuzzy, the notion of trying to force modeling of imprecise language by a very, very precise set theory is maybe sometimes too constraining. So Lofty-Zadeh, who's a computer scientist, artificial intelligence person at University of Berkeley, developed this idea of fuzzy set, which basically said that membership in a set is gradual. So, for example, is football a sport? Everyone says yes. Is swimming a sport? Yes. Is backgammon a sport? Is chess a sport? So, I mean, so the membership of certain exemplars in categories is clearly not always 0-1. So we've been working, for example, with, in this context, using, so these are membership functions, right? So membership functions are essentially, it means that for every, so let's look at one. This is the word likely. This is a hypothetical membership of what likely means. In other words, if it's 0, it's definitely not in the concept likely. If it peaks, that means that this is the prototypical meaning of likely, and all other levels, it means that it's, you know, it's somewhat or sometimes under certain circumstances likely. And so you can measure, you can, you know, scale these membership functions, and you can basically do a lot of theorizing with them. So for example, if you have a lot of time and energy, if it's important to you, we showed in experiments that if you want to take probability words in one language, let's say in French, and you want to communicate them to someone who speaks another language, let's say Turkish, rather than say, looking at a French-Turkish dictionary and say, well, what does possible means in Turkish, right? You can map people's membership functions, and you can assign a translation based not on the vocabulary, I mean, the dictionary meaning of the word, but on the degree to which membership function of a French-speaking person and a Turkish-speaking person of various words are. So in other words, I may say one word in French, I'm going to choose to tell you the one word in Turkish whose probability, whose membership functions matches as closely as possible the one I used, and you can improve communication considerably by these means. So it's exactly 10:30, so I can claim 5 minutes because I started late. So I'd like to go back. I mean, I'm not even asking you what you want, okay? So I'm just, here's what I'll do. So I feel bad that I didn't say anything about risk. Okay. Let me try. So, did you ever send reports to Microsoft? Did they ever send you anything back other than more requests? So I wanted to give you something about risk. I mean, I like to talk about uncertainty more about risk because I really know much more about it, and I should have told you that before I agreed to come. But I do want to show you something about risk. So as remember, I said when we talk about risk, we talk about risks. We really don't mean only the uncertainty, but it's kind of the totality of certain hazards, right? Which invoke how likely they are to occur, to encounter them or to meet them, and also how severe they are. And so all this work, the great work around this was done by Baruch Fishoff at Carnegie Mellon and Paul Slovic at University of Oregon. And so here are some key interesting results, which I'm sure some of you have seen, and maybe not everyone. So the whole idea is that every single risk, in this particular case you have two risks, one is nuclear power and the other one is X-rays, has a different profile in the sense that they identify these various attributes. The list this is a partial list. You can add things, you can take out things. So in this case, they ask whether exposure to X-rays or nuclear power is voluntary and involuntary. So typically, in this case, clearly, people undergo X-rays voluntarily, not so exposure to nuclear power. How catastrophic, how common, how known, how understood, how immediate or delayed the consequences are. So you can have a profile for every single risk. So what they've done, they collected data from the public on profiles of this type for many, many, many risks, and then they map them. They do, I can't remember whether they did a factor analysis or an MDS, and do you even know the difference? Does anyone know the difference? But essentially, here's what this is, the way to think about this is the following, is that, if you have a map, you can take 2 points on the map and measure the distance between them, right? Now imagine now that we have to do the reverse map problem. You don't have a map, you just have a list of distances. Now you take these distances and try to recreate a map such that the points will be placed in such a way that the closer they are on the map, that means the closer they are in perception. So this is essentially, let's say this is a multidimensional scaling, a 2-dimensional scaling map of perceptions of risk, in the sense there are 2 things to talk about this here. One is that points that are together mean that they are on average very close to each other. They are perceived to be equally risky or not risky. Second, that's one thing. The other thing, they create a configuration that you can interpret it, for example, by finding a set of axes, right, that are meaningful and that tell you what are the features of these things that are up there in the northeast or things which are in the southwest and so on. And then basically you try to make sense of this configuration by understanding what are the common features or the factors that drive this representation. So these are about 50 risks that are put together. And the key factor, the thing that explains the higher amount of variance, because the way this is done through a singular value. You create this large matrix of similarities or proximity, submit them to a singular value decomposition. So you maximize the variance on the first dimension, and then you maximize the variance on the second dimension, subject to being orthogonal to the first, and so on. And so the key factor, the one that goes from left to right, which is the factor of dread. Okay? Or how catastrophic, how dreadful, how bad things are. Maybe there's another one which is easier maybe to read. And so dreaded and not dreaded. And on the other hand, the second factor is the degree to which it is known and unknown. And the third one, which sometimes shows up, not always, is this issue of how voluntary it is. But how voluntary it is, it's quite often, it's quite highly correlated with known, because people, only expose themselves voluntarily to think that they actually know. So this idea is that it shows you how people think of risk, and clearly, of course, this can be different. These are just some typical examples, just a very stylized version of the previous of the larger table, is that people's perceptions of risk are not necessarily objectively correct. Not correct, I say. They are not in line or aligned with the objective, dangers to life or probability of exposure to harm, but they are really driven by other factors which are not necessarily the factors that are more psychological rather than objective measures or analytical measures of risk. And so so the question is risk, should we perceive risk? Is it an analysis or is it a feeling? Okay? And so I alluded earlier to Danny Kahneman's book, but this is, he has kind of wrote a very, very nice description. It really originates in other people, this idea that there are two modes of thinking. I mean, it's a very amorphous. I mean, it's not precisely defined. It's not that we can say, well, there's the area of the brain that corresponds to the experiential and the other one that's to deliberate. But it's just a sense that, decisions can be by what I call system one, which is fast, associative, based on feeling, based on stories, based on images, and intuitive. And system two, that is more deliberative, logical, reasoned. And the way we think now about many of our results is that instantaneously system one immediately faster reacts and has a reaction. And in many cases, system two, which is kind of overrules it or basically operates on top of system one and corrects some of the mistake or some of the decisions of system one, but not always. And so the whole idea is that I'm not going to go any more further. Is that when it comes to risk, for most people, in most cases, it is clearly the system two, the more effective one, that drives people's perception of risk, and not a statistical, reasoned, detailed analysis of the actuarial or other risks associated with it. So I'm already gone over my time. I'm going to stop here, but I'm still very happy to answer questions that you might have.